Okay, how's everyone doing? So, just a note, I for the homework, I graded like 2 out of the 4, right? For the first one. So I graded the not symmetric but transitive and reflexive one, and then the induction divisible by 3 one. So 5 points each. So yeah. Any questions so far? Okay, if not, we're gonna go into the what do you call it? More into groups. So someone emailed me about the GCD LCM thing. So I mean, you could just prove GCD of AB times LCM of AB equals A times B, and then that homework question should just follow. So I don't think it's that hard to prove. You just use the fundamental theorem of arithmetic. Okay, let's get started. So we're going to talk about first about cyclic groups. So these are groups, if you think of it like groups generated by one element. Now, what do I mean by this? I mean, take an element of your group, take all powers of it, including the negative powers. So by negative powers, I mean the inverse, right? You take all powers of your element, and then you take all powers of its inverse. And if you get the whole group, it's cyclic. Yeah, so example would be integers. So why are the integers cyclic? Well, it's generated, people we write generated, we write like this, less than and then greater than. So why is this cyclic? So this is cyclic because it's generated by 1, right? You can get any integer by powers of 1. Like 5 is, 1 to the 5th, right? So again, this is integers under addition, right? Because this is 1 plus 1 plus 1 plus 1 plus 1. And negative 1 is 1 inverse, right? Because 1 plus negative 1 is 0. So negative 1 is the inverse of 1, right? Now you can get negative 2. Well, using the law of exponents I talked about last time, this is 1 to the negative 2, right? Because this is 1 to the negative 1 squared, which is negative 1 plus negative 1, which is negative 2, right? Because the thing inside is negative 1. So you could get every integer by 1, right? So the integers are cyclic. So everyone good so far? Okay. Now there could be, a choice of generator, right? There's no reason why I chose 1, right? It's also generated by negative 1, if you want to think of it the other way, right? Because the inverse of negative 1 is 1. But it can't be generated by anything else, right? It's in this case, there's 2 possible generators you could choose from. Okay, now z mod nz, yeah, the remainder is mod n. Hopefully it's clear it's generated by 1, right? Because the remainders mod n are 0 all the way to n minus 1, right? So it's clear you can get, if you like, 1 to the 0 is 0, but if you don't like that, 1 to the n is the class of n, and n has remainder 0 when dividing by n, right? So however you want to think about it, it's also 1 to the 0, right? And so you get every element, right, by taking the class of 1. So question, can you describe all the, how do I say it? Anyways, let me just leave it at this. So it turns out that I believe that all numbers co-prime to n are possible generators, but let's let's not get into that. Just know that Z mod NZ is generated by 1. So question, are cyclic groups abelian? What do you all think? So remember, abelian is, you know, GH is HG for all, right? Things commute. So do things commute in cyclic groups? Yeah, it does, right? So how do we show this? So let G be cyclic. So since G is cyclic, G is generated by one element. Let's call it A. Yeah. Now let GH be arbitrary elements in G. Then by definition, G is A to some power and H is A to some power. Yeah, I don't know. Let's use J, right? But that's what it means to be cyclic, right? Every element is a power of something, of your generator. So from here, right, it's clear that it's abelian, right? Because what is GH? GH is AK times A to the J, which is A to the K, and then you use the law of exponents, right? If you I don't think I even need this step, but it's pretty clear that this is true, right? And then that's HG. Yeah. So you see that it goes like this: cyclic groups, subset of abelian groups. So not all abelian groups are cyclic, but it's a subset, and then you have groups. Yeah. So cyclic groups are special. So given a group G, you can have a cyclic subgroup, right? You have a cyclic subgroup. So what is the cyclic subgroup? Well, take an element of G, any element, and then just consider all powers of it. That is a subgroup, right? So if your group is not cyclic, then this G will not generate all of the whole group, right? But it still generates a subgroup. So yeah, so you can always have a cyclic subgroup by just taking one element and then just taking all powers of it, right? So and then let me just write take the group generated by G. Everyone clear so far? Okay, let's move on. We're going to go over more examples of cyclic subgroups. So let's learn about complex numbers. So complex numbers are the set of A plus BI. Hopefully this is all review. A, B, and R, right? And then if Z is A plus BI, the absolute value of Z is square root of A squared plus B squared, right? And we certainly, let me just write if absolute value, if we call absolute value of Z R, then we could write this as in polar coordinates is R cosine theta plus R I times R sine theta, right? And some people write it like R e to the I theta, right? So that this is let me just write this is, I think people call it rectangular coordinates. And then this is polar coordinates, right? And it's clear that this is your X. I mean, this is your A. This is your B. Yeah. So just to, rectangular is like just a picture, right? If this is your x-axis, y-axis, sort of, right? This has A and this is B. So this is your I'll call it the imaginary axis. I think that's better. Imaginary axis and then real axis. Yeah, so A plus BI is this point. But you can also go another way, right? You could say how much of an angle you make, theta, and then you go R, right? And then this is your radius, right? And then if you use trig, you'll figure out that, you use sine and cosine to get the polar part. Yeah, so there's two different ways of expressing a point on the complex plane, right? Everyone clear so far? Hopefully that's all review. So here, so we could consider a subset. We could consider the unit circle. So let T ooh, what am I doing? Okay, let T equal the set of Z and C such that absolute value of Z is 1. So picture-wise, what is this? Oh, can you move up a little? Is this good? I'll wait like 5-10 seconds. You good? Okay. So what is this set picture-wise? Picture-wise, what is the set of, elements of absolute value 1? So this is what? This is square root of a squared plus b squared equals 1. How do you graph this? If I square both sides, I still get 1. How do you graph this thing? I guess if I write it like this, it should be more clear. Yeah. Some people view the circle, I guess any ellipse where these two numbers on the bottom are different, but if they're the same, it's a circle, right? So, I mean, so here it's a circle of radius 1. And what you're going to see is this forms a group under multiplication, right? So why is that the case? It's because it's due to the fact that this is true, right? The absolute value of A times B is absolute value of A times absolute value of B. And then since they're both 1, this is 1 times 1. So the product remains in T, yeah? You see, it doesn't really hold for absolute value 2 or whatever, right? Only holds for like the unit circle. So this is, yeah. And you could check that, if two elements multiply to 1, right? Z times Z inverse equals 1. Then taking norm on both sides, right? The norm of 1 is 1. This thing we assume was in G. right? So that this is norm 1, so this forces norm of Z inverse to be 1, right? So you see Z inverse is in T, yeah? So, I mean, and then hopefully associativity is easy, right? Identity elements 1, and this thing shows your inverse belongs to your group, yeah? So this thing is a group under multiplication. Everyone clear? Yeah, it's a circle. Unit circle, to be more precise. So, but let's consider a subgroup of this. So, consider the set. Let me just write. How should I write this? Tn. I forgot how the book denotes it. To be the set of Z and C, such that Z to the n is 1. Yeah. So it's a number satisfying this equation. Now, let's be clear. Over C, this thing has n roots, and they are called the roots of these. The roots of these of this equation. Bad English. Of this equation is called the n fruits of unity, right? Of unity. So from here, right, note that all of these belong to the unit circle, right? So it's a subset of T, right? This thing belongs to the unit circle because if Z to the n is 1, then this thing is absolute value of what if I take absolute value on both sides, and a number to the nth power is 1. Like, note that absolute value is a real number, right? It's not complex anymore. So it forces absolute value of Z to be 1. Yeah. So these are subsets of T, right? Now, how do they look like? So if you go back to your thing, they look like this, right? So the roots of the nth roots of unity are e to the 2 pi I over n, right? 2 pi I k, right? Where k runs from, there's a convention, the book goes with 1 to n. Now, really quickly, why do we only, if these are all of it, why are these all of it, and why do we not have any more, right? So these are all of it because, I mean, if you take k to be bigger than n, let's say k is n plus 1, it actually corresponds to k equals 1, right? Because why is that the case? Well, if I take n plus 1, this is e to the 2 pi I over n. What am I doing? Yes. If I foil, I'm really bad at foiling. Let me see. It's e to the 2 pi I. E to the 2 pi I plus 2 pi I over n, right? Now, this thing is e to the 2 by, property of exponent. This is, you get this, right? Now, this is when k is 1, right? Do you agree? Because if I plug in k equals 1 to here, that's what I get. Now, what is this term? Well, this term is actually just 1. Why? Because if I go back to this thing, right, forget the r. R is 1, right? Because it's unit circle. So e to the I theta is cosine theta plus I sine theta. Yeah? Now, so this is cosine of 2 pi plus I sine of 2 pi. Sine of 2 pi is 0, right? And cosine of 2 pi is 1. Yeah. So you see, these are all of it. So, and I mean, you can't have any more, is what I'm saying. And why are these all of it? Well, it's an equation it's a degree n equation, right? So a degree n equation over C has at most has n roots. Yeah, let's put it that way. I mean, over R, it could have at most that, right? But you can't have any more, right? Like, for example, x squared plus 1, the roots are I and minus I, but it's not in R, so there's 0 roots in R, but there's 2 roots in C. But in general, you could only have at most n roots, right, over C, and for a degree n polynomial equation. So these are all of it. And so from here, these are cyclic, right? This group is cyclic. So Tn is cyclic. It's generated by, hopefully it's clear, it's generated by e to the 2 pi I over n, right? When k is 1, right? Because when k is, I mean, and then if you take powers of it, that's when you vary k, right? When the square is when k is 2. The cube of this element is when k is 3, and so on and so forth. So this is an example of a cyclic group. So is everyone clear so far? Okay. So picture-wise, it splits the circle into whatever you have. Yeah. So let's do an example. So like z cubed equals 1, right? This is z cubed minus 1, which is z minus 1. I forgot what the formula was. I think it was something like this, right? Something like that, right? I forgot the difference of cube formula. But anyway, you get this, right? So it sort of splits the unit circle into 3, I guess. Looks, I'm not good at drawing. Let me just, what is this? I mean, it's e to the 2 pi I over 3, right? So, really bad with trig right now, but you get this. So if I think about it, 2 pi over 3, that is, so your first root is 1, so it's right here. So I'm gonna guess it's like, it looks something like this. Yeah, for the 3, for the T3. Yeah. So okay. So your e to the 2 pi I over 3 and e to the 4 pi I, the second power, are the roots of this thing, right? And e to the 6 pi I over 3 is e to the 2 pi I, and then we showed before it's 1, right? So that's the root of this thing. Okay, so be careful. The fact that degree n equation has n roots at most, I mean, it does have n roots, but you can't have any more. That's not true if you move to a different thing. Yeah, let me just give an example. Like x squared is 1 over, like, if you just consider this over z mod 8z, yeah, this has 4 solutions, right? Like 1 squared is 1, 3 squared is 9, but 9 mod 8 is, let me write congruent, right? 9 mod 8 is what? 9 mod 8 is 1. And then from 5 squared is 25. 25 mod 8 is 1. And 7 squared is 49. 49 mod 8 is 1. Yeah. So you see this equation has like 4 solutions in z mod 8z. but it's a degree 2 equation. So, you know, it's not true if you change this thing. Yeah. I mean, the fact that it's C is important. Okay. Any questions so far? Okay. So that's an example of a cyclic group. Yeah, the roots of unity. Okay, now moving on, we're going to move to something new. It's called permutations. So permutation on set of n elements. So this is another example of a group. So what is this? This is a bijective map. If I to reinterpret this, it's bijective map from 1 to n to 1 to n. So in other words, hopefully you all know what bijective means, right? It's injective and surjective. In other words, it's invertible. Yeah. So what are all the ways? Let's consider. Then we call it the set of permutations on n elements. We call it Sn. Yeah. So this, and then turns out it forms a group under composition. So let's see what it is, right? So let's see S3, right? 1, 2, 3, 1, 2, 3. What are all possible ways you could, what are all possible bijective maps, right? I can send this to this, this to this, this to this, right? So this is the identity, yeah? And I better have an identity or else it won't be a group. So next, I can move 1 to 2, 2 to 1, and then keep 3, yeah? So in other words, I'm moving 1 to 2, and then 2 back to 1. Yeah, so we write it like this. And then what else can I have? I could have 1 to 3, 3 to 1, and then keep 2 the same, right? So here I'm swapping 1 and 3. Actually, let me just keep it on the same page. Okay, so what else? I can move 1 to 2, 2 to 3, and then 3 to 1, right? So 1 goes to 2, what does 2 go? 2 goes to 3, and then 3, when you read this, 3 goes back to 1, right? So you read it like this. Same for here, right? You go here, and then at the end, you go back to the first term. Okay, and then I can also have, let me think, 1 to 3, and then 3 to 2, and then 2 to 1, right? So 1 goes to 3. Where does 3 go? 3 goes to 2, and then 2 goes back to 1. And finally, I can have, what else? 2, 3, right? So 1 gets fixed, 2 and 3 get swapped. Yeah, so these are all of it. So is everyone clear on this? So again, you can't do like 1 to 2, 2 to 2, right? You have to, it has to be different because this thing will contradict injectivity, right? Right, because two things get mapped to the same thing, and then it will not be a bijective map anymore. And similarly, you can't just map everything to like 1, right? Because it contradicts surjectivity, right? So it won't be bijective, right? Surjectivity means you have to hit every element in your range. So it won't be a permutation. So these are all of it. for S3 at least. Everyone good so far? Okay, great. And it turns out S4, you know, you can actually just think of all of it. I could write it out. So identity, and then you have the 2 cycles, 1, 3, 1, 4. These should be commas. And then you have the product of 2 cycles. So these are called cycles, yeah. These are, I'll go over cycle notation later, right? You could go 1 to 2, 3 to 4, or 1 to 3, and then 2 to 4. Or you could go 1 to 4, 2 to 3. You can have 1, 2, 3, 1, 3, 2. I'm just gonna put dot, 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 yeah. And then there you can also have 1, 2, 3, you know, stuff like this, right? So it turns out there's 4 factorial of these. And then you can see here, this is 3 factorial, right? The size of this is 3 factorial. 3 times 2 times 1, which is 6, right? So you see it grows pretty big here. So in general, the size of Sn is n factorial. Yeah. So next thing is I want to go over what cycle notation means. Yeah. So when I write, these are called cycle notation, right? To index my map. When I write like A1, A2, dot, 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 AK, this means A1 goes to A2. Let's assume, you know, it's ordered. A2 goes to A3, dot, 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 AK minus 1 goes to AK, and then AK goes back to A1. Yeah, you can always represent a permutation in cycle notation. Yeah, so let me just go over, for example, S4, when I have 1, 2, 3, 4, 1, 2, 3, 4. So how you, if 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. You start with any element, right? Start with 1. Then you ask yourself, where does 1 go? Okay, from this thing, 1 goes to 2. Okay, now you ask yourself, where does 2 go? 2 gets mapped back to 1. If it maps back to the element, you close it. And then you go to your next element. Start with 3. Where does 3 go? Well, 3 goes to 4. And then you ask, where does 4 go? 4 goes to 3. So this is the cycle notation for this map. Yeah. And then really quickly, let's just 1 to 2, 2 to 3, 3 to 4, 4 to 1. Yeah, so again, you start off with 1. You could start off with 2 if you like. I'm just going to start off with 1. So from here, 1 goes to what? 1 goes to 2. And then you ask yourself, where does 2 go? 2 goes to 3. And then where does 3 go? 3 goes to 4. And then where does 4 go? 4 goes to 1. So you close it. Yeah. If you want to start with 2, we could do that. So then you ask yourself, where does 2 go? 2 goes to 3. Then you ask yourself, where does 3 go? 3 goes to 4. Then where does 4 go? 4 goes to 1. And then where does 1 go? 1 goes back to 2, right? So you close it. So these 2 are equal. Yeah. I mean, there's many ways to represent it. But yeah. So is everyone clear on cycle notation? Like, it's pretty important you understand cycle notation, because SN is like one of the most studied groups in like group theory. So you must know cycle notation. Okay. Any questions? Okay. So moving on. 2 cycles are disjoint. This definition. Disjoint. If basically they don't have the same, they don't share a common in our case, number. So if sigma equals A1 to AN, tau is B1 to BL. Do I want N? Let me use K. Yeah. It's if AI is not equal to BJ for all IJ. So an example would be in S, maybe S5, let's make it bigger, right? 1, 2, 3, and 4, 5 are disjoint. Because they don't share the same thing, right? I mean, they don't share the same number in our case, right? So an example of something that's not disjoint is 1, 2, 3, and I don't know, 3, 5, yeah, are not disjoint. Because they both have the element 3. So why is this important? Well, things in Sn is an example of a non-abelian group. Sn not abelian. So maybe to see this, let's, I don't know, let's compose something. I didn't try this yet, so let's try to find an example of why it's not abelian. So before that, I have to tell you group operation, right? How do you sort of do the group operation, right? I didn't really tell you, because if I don't tell you the group operation, this makes no sense, right? So let's do an example. So if I have the element, what elements were there in S3? Let's pick some. S3 are these 6, right? So let's work with 1, 2, 3, and 2, 3. Yeah. So the order matters, right? So 1, 2, 3, circle 2, 3. Most authors will just write this. Yeah. So what you do is, again, you start with something, right? So in our case, let's start with 2 if you like. So you read like right to like left. So you ask yourself, where does 2 go? 2 goes to 3. Then you move here. Where does 3 go? 3 goes to 2. So it goes back to the same element. So you close it. So and then from here, you start with 1. You ask, where does 1 go? Well, 1 does not, lie in here, right? So 1, only goes to 2. Well, hold on, let me think. Did I make a mistake? No, 3 goes to 1. Ooh, my bad. I'm dumb. Okay, so let's go back. Made a mistake. So here, if I start with 2, 2 goes to 3, and then 3 goes to 1. Yeah. So 2 goes to 1. And then you ask yourself, where does 1 go? 1 goes to 2. Yeah. So you close it. And then you could check 3 goes nowhere. So you don't need to write anything. So let's do another example. I don't know. Let's do the same thing. Right. Or 1, 3, 2, 2, 3. So again, pick a number. If you like, let's start with 1 this time. 1 does not appear here. So we move on to the left one. 1 goes to 3, right? And then now you ask yourself, where does 3 go? Well, 3 goes to 2, and then where does 2 go? 2 goes back to 1, right? So 3 goes back to 1. So you get this, yeah. And then you could check that 2 goes to the same place, right? So you don't need to write it. For example, 2 here. If I just work with 2. 2 goes to 3, and then from here 3 goes back to 2, right? So 2 just gets mapped to 2, so you don't really need to write it. Nothing changes for 2. Is everyone? clear so far? So why do we read right to left? That's just convention. Yeah, that's how most books do it. So knowing this, let me ask 2, 3, 1, 2, 3. Let me see what this is, right? So from here, let's start with 1. Where does 1 go? 1 goes to 2, 2 goes to 3. Okay, now let me erase. So now we ask, where does 3 go? From here, 3 goes back to 1, and here nothing happens, right? I mean, there's no 1 here, so you close it. And then you could check 2 goes to itself, right? Because 2 goes to 3, and then 3 goes back to 2, right? So you get 1, 3. So what do you notice? Can anyone tell me? What did I just compute here and here? Right? So I took the element 1, 2, 3. I did the group operation with 2, 3, and I got 2, 1. I reversed it, and I got 1, 3. Yeah? So this shows S3 is not abelian, right? I forgot what the book read. The books, I think they might have wrote non-abelian. Same thing, yeah? So your cycles do not commute, yeah? Is everyone good so far? Which part? Which part? Like this part, Zoo? The part I just boxed? Like this part? Is that what you want me to explain? Oh, yeah. If you like, you can write. Basically, if things don't go to themselves, if you don't write anything for if there's no 3, it just means that it goes back to itself. Yeah, I mean, if you like, you can write this, right? If you want to include everything, this just means 3 goes back to itself, 2 goes back to itself, 2 goes back to itself, right? But it's redundant. Yeah, I mean, so when you first do it, you'll get this, right? But I mean, it's by convention. If like things go back to itself, you don't really need to write it. Yeah, it's only when things get moved to something else. Like if 1 doesn't go back to 1, so we have to include it. But if like 3 goes back to 3, then it's kind of redundant to like write it. That's all. Yeah, are you good? It's just convention. And then move to, it's like, oh, the Y2 goes, yeah, you read left to right. So for example, let me just do something. Oh, I have erase on. Let's do something bigger. Yeah, 1, 2, 5, 4. Let's do it in S5. Yeah. So if I have 2, these are 2 elements in S5. Yeah, 1, 2, 3. Yeah. So what you do is you pick a number. You start with 1. Let's start with 1. Then you ask, where does 1 go? And you read right to left. So you find a 1. You read where it goes. It goes to 2. Yeah. And then where does 2 go? You start with 2. It goes to 4. So 1 goes to 4. Now you start again. You start with 4 and ask where it goes. There's no 4 here. Yeah. So again, you read right to left. There's no 4 here, so now you move here. Where does 4 go? 4 goes to 5. And then you start over again. You ask, where does 5 go? There's no 5 here, So you move left. There's a 5 here. 5 goes to 3. Oh, sorry. I don't know why I closed that. And then you ask, where does 3 go? Okay, 3 here goes back to 1. And then you ask, where does 1 go? 1 goes to 2. So this is the cycle 1, 4, 5, 3, 2. Clear? Okay, great. Really important you understand this. So,
Hi, Matthew. Can you hear
yes,
me?
yeah.
I still don't kind of understand, like, because 1 goes to 2 at the very first time, then why don't you?
But you're not done, right? You have to read right to left, right? So what I mean is, once you read 1 goes to 2, you still need to see where 2 goes here.
Yeah.
Yeah. So 2 goes to 4. So 1 goes to 2, 2 goes to 4. So 1 goes to 4. So I get this.
Okay.
And then you ask, where does 4 go? So
To 5.
4 goes to 5. So I have 4 to 5 here. And then you ask, where does 5 go?
I think I understand.
5 goes to 3. And then you ask, where does 3 go? Well, 3 goes back to 1. And then 1 goes to 2. So 3 goes to 2.
Okay.
Yeah, and then I closed it because that's all. I mean, if you like, you can check 2 goes back to 1. But, I mean, let's just do it for practice. 2 goes to 1. 2 goes to 3, right? And then 3 goes back to 1. So 2 goes to 1.
Yeah.
Okay.
Okay, thank you.
Okay, everyone clear on cycle notation? Okay. I mean, took some time, but it's good we all get it. But in general, you see that this thing is not abelian, right? Because 1, 2, 3 group operation 2, 3 is not 2, 3 group operation 1, 2, 3, right? I mean, in general, I mean, if you compose 2 functions, right, you should not expect these 2 to be like the same, right? So it makes sense. Now, why I mean by disjoint cycles? So I can always write a product of cycles as disjoint cycles, right? So here is an example of me writing product of this product of 2 cycles. Let me just say product of cycles into disjoint cycle. Right? So right here is not disjoint, right? Like this cycle notation, I mean, these 2 are equal, right? But the left-hand side is not disjoint, right? Like there's a 2 here and there's a 2 here. There's a 3 here and there's a 3 here. In fact, there's a 1 here and there's a 1 here. But after doing, but this is just shorthand for this, and this is a disjoint cycle, right? I mean, there's only 1, so of course it's disjoint. But you can always write everything in terms of disjoint cycle notation. So it's nicer. So why do we like this? It's because disjoint cycles commute. So what I mean by this, if you have 1, 2, 3, and then 4, 5, it is what it is. Yeah, this is 4, 5, 1, 2, 3. And I mean, the reasoning is because they don't affect each other. Yeah, when we do this operation, right here, it could be like 2 gets moved somewhere and then 3 gets moved somewhere. But here, like they really don't share any number. So it's pretty clear that they commute. So you see for the example, I showed that where they don't commute, these 2 were not disjoint, right? Both of them have a 2 in it and both of them have a 3 in it. So for if you want to show Sn is not abelian, you should choose non-disjoint cycles. Yeah, because disjoint cycles will commute. Everyone clear? So let me just go. I'm out of time. Okay. I'll just save transpositions for later. And sorry for my phone. I get like commercial calls sometimes.